Have you ever wondered why you can put this in your recycling bin, but not this? Why can this be made into new products, but this will go into a landfill? And what about these? Why is it that you can recycle this if you live in one of these places, but not if you live in one of these? One reason is that there are nearly 10,000 separate recycling systems in the United States. Each makes their own rules. And while a majority of Americans support the idea of a uniform standard for recycling, no such standards exist. As a result, curbside recycling is a bit of a mess. In a 2019 survey by the Consumer Brands Association, Americans ranked recycling as more confusing than assembling IKEA furniture or doing their taxes. And recovery rates show it, with nearly 62% of American household waste being sent to landfills or incinerators. So how did we get here? And more importantly, how do we turn things around? Confusion around recycling isn't entirely an accident, and its most fundamental element may have been looming in plain sight all along, in the form of this symbol. The Chasing Arrows graphic was the winning entry of a design competition for the very first Earth Day in 1970. The concept was to represent paper recycling, and because of the nature of the competition, the design remained in the public domain, unable to be trademarked or regulated. By the late 1980s, the symbol was universally associated with recycling of all types, and the Plastics Industry Association issued a new set of symbols with a suspiciously similar design. The resin identification codes combine the Chasing Arrows design with a number indicating one of 7 common types of plastic. And while widely considered to be a recycling code, the symbol itself makes no guarantee of recyclability. Today, there are nearly 100 variations of the symbol in use, along with dozens of other vaguely environmental messages, like the fact that the manufacturer contributes money to recycling programs, or simply discourages littering.
Consumer brands know people want to do right by the environment, and so they're now putting lots more messaging on their products to make the product feel more eco-friendly. There's very little standardization associated with claims that are made. There were some things like the recycling symbol that people were using that there were no rules.
California State Senator Ben Allen authored the Truth in Labeling bill, prohibiting manufacturers from using the Chasing Arrows symbol on products that can't factually be recycled. And for California, that doesn't mean in just a few specialized facilities. It means in curbside pickup bins anywhere in the state.
And we know what's going on, right? They're trying to associate their product with the feel-good aspect of environmentalism. And yet they're actually acting in a grotesquely irresponsible way by putting that recycling symbol on their item. What it does is it encourages people to feel good about the product and then put that item in the recycling bin. And if anything, by having them in the recycling bin, they're actually contaminating the system. You're throwing a lot of extraneous material in there that makes it harder for the system to work. It means that you have to have a whole infrastructure in place to sort out those items that are truly recyclable from those that are not. So anything we can do to ensure that we have a cleaner stream of materials going through the recycling system, it actually gives our recycling system a fighting chance of doing its job. It's a basic question of truth in advertising. And so our bill said, we're not gonna let you use the recycling symbol if your item's not recyclable. But we haven't fixed the problem. This is a good bill, I'm proud of this bill, but all it does is ensure that people aren't being actively deceived. There's a much bigger problem here that we need to address.
America is in the middle of a recycling crisis.
The price of new virgin plastic is actually cheaper than buying recycled plastic right now.
Processing costs have gone up, and the price you can sell the commodities for on the back end has gone down.
Most recycling programs across America are upside down economically.
Recycling changed forever in 2018. Prior to this, the vast majority of American waste was exported to China for recycling. But the reality of the situation was far more complicated.
We were all living a lie. We were basically just exporting our problem. It was cheap to do because ships would come from China filled with plastic products and cheap goods. And then the ships would have to go back to China and they'd have all these empty shipping containers. What are you going to fill them with? So a lot of this trash ended up in these shipping containers sent back to China. Bales would show up of supposedly recyclable material. Little ships would take them up rivers, and villagers would come out, and they'd get a bale, and they'd sort them themselves. And they'd basically sort out whatever they could sell. And the rest of the material was getting thrown into the river. It was getting burned. It was creating a lot of ecological problems. So the Chinese said, enough is enough. This stuff is too contaminated. We are bringing down the national sword, that was the name of this policy, and stopping the import of all of this trash. And that created a major crisis on our side.
Markets changed immediately overnight here in the US. This is not just a valve that you can turn on and turn off. Prices plummeted to record lows, and it ultimately trickled down to communities that began to either contract what they were collecting or stopped collecting recyclables altogether.
Kim Holmes is one of the many experts who helped U.S. companies navigate the collapse of the domestic recycling market. But her work is far from over, as the repercussions of China's national sword policy are still being felt around the world.
It shined a light on our domestic recycling infrastructure that, frankly, it wasn't adequate. And there became this larger question of whether it was worth it. It really kind of shook the faith and foundation in recycling. It felt like recycling was failing, but we couldn't let that happen.
And thus began the race to rescue recycling. If the system was to survive at all, the linear economy model of take, make, and waste would have to be re-envisioned in a fully circular way.
What is the goal of the circular economy? It is truly to find the pathways to keep all of the resources that we have at our disposal, that we have in play, and keep them in play. Could we build everything that we need from the things that we already have today by matching the right innovation with the right materials that we have? So that means we are no longer extracting and wasting. What if we had enough technologies at our disposal that we could find value in all of the plastic items that we use today? And there was a future where all the plastics we use goes into our recycling bin, and we have the technologies and the opportunities to recover the value from that rather than sending those valuable resources to the landfill.
Yet the main barrier to achieving this goal is the same as it was in 2018: contamination. But not just the obvious types of contamination, like hazardous waste or rotting food. It's contamination as a result of having more material types on the market than can feasibly be kept separated. Over the last decade, manufacturers have increasingly adopted composite packaging made of multiple layers of different material. Paper coated with plastic, plastic lined with aluminum, countless combinations, each difficult or impossible to separate. As composite packaging multiplied, the task of sorting each product type was no longer humanly possible. So engineers began working on a different problem: how to take humans out of the equation.
So the way a typical recycling facility is built, they use what are effectively large pieces of mining equipment to try to separate out different commodities. But unfortunately, they're not very accurate. Plastic bottles are in with the paper. Aluminum cans are in with the plastic bottles. So what the recycling facilities have to do is they surround this equipment with people to basically correct the mistakes that those pieces of machinery make. You might see 20, sometimes even 30 people working per shift, sorting stuff by hand. People put all sorts of nasty stuff in the recycling. Rotting food is an obvious one, but also hypodermic needles, knives, diapers, this sort of thing. The result is it's a pretty tough job and has high turnover, and that's where our robots come in to help.
Matanya Horowitz is the founder of Denver, Colorado's AMP Robotics. His vision is for AI to shift the economics of recycling on a global scale.
We aren't the first to see the potential for robotics in the recycling industry. In fact, the robots we use have been around for a while. Really, the missing ingredient has been a vision system that can identify this material and say, that's a bottle, that's a can. We have created a vision system that can do that, built on artificial intelligence. It can learn to identify pretty much anything you or me can be taught to identify, just something as specific as a Starbucks cup or Captain Crunch cereal. This system can actually learn to identify those things. What it allows us to do is sort the material the recycling industry sorts today, but we can go a lot further. If we can identify something as, say, a cottage cheese container, we can start to do things like separate out nothing but the cottage cheese containers or nothing but the coffee pods. The reason that's interesting is that this packaging tends to have a more consistent chemistry if it has a common use. And if you can deliver materials with a common chemistry, it ends up having significantly more value. And the more value there is, the more people will want to go after that material and not let it get into the oceans and not let it get into a landfill. And it ends up, AI opens that up because it can identify things at this very precise level, which is much the same way as you or me would learn to identify these things. When new packaging gets introduced, it gets incorporated into the data set, and we push an update out to the whole fleet, and they all learn from that. So the result is that our robots here in the States, they're learning from the packaging in Japan, and those are learning from the packaging in Europe. It's going to be this huge task, but over the next couple of years, we're going to continue to basically learn every form of packaging there is in the world. What we're all about is improving the fundamental economics of the recycling process. There's a tremendous amount of value, hundreds of billions of dollars worth of material that's being thrown away each year because it costs over hundreds of billions of dollars to extract it all. If we can reduce that cost, people are naturally going to go after it. If we can do that and make it, in particular, more lucrative than landfilling it or incinerating it, there is a natural economic incentive for people to build businesses around extracting all of this material value. And that's ultimately what we want to be able to do, is help the world divert 80%, 85% of the material stream. You contrast that with the reality today. Under 10% of the plastics the world produces are actually recycled each year. If you can bring that number up to 80%, and in particular, when you look at what the carbon implications of that are, it's actually massive. You're talking about the same order of magnitude as something like the electrification of transportation as the impact of diverting that much stuff. And we really think that's possible if you set up the incentives right.
But even if all waste sorting was automated, how close would we come to closing the loop and achieving true circularity? According to experts, not close enough. The reason is that conventional mechanical recycling still lacks the ability to handle many types of plastics, and the types it can handle degrade in each successive generation, until the only option is the landfill. To delay the inevitable, manufacturers simply blend recycled plastic with a steady stream of new virgin plastic, produced from freshly extracted oil and gas. To break free from fossil fuels for good, recycling itself needs an upgrade. And that's exactly what's taking place a few miles away at Boulder, Colorado's National Renewable Energy Lab.
The absolute magnitude of plastics that are made today that cannot be recycled through mechanical recycling is vast, including carpet, clothing, and all kinds of other things. And that's where advanced recycling technologies have a massive potential role to play.
Greg Beckham and Kat Knauer are two of the leading researchers at the U.S. Department of Energy's consortium on biooptimized technologies to keep thermoplastics out of landfills and the environment, otherwise known as bottle. Their work takes aim at the long-standing challenge that the plastics we use today simply weren't designed with recycling in mind.
With mechanical recycling, your plastic water bottle is just chopped up, melted down, and reformed into potentially another plastic water bottle or perhaps something different. And structurally, nothing changes in the material. This type of recycling is also very, very, very limited by any kind of contamination. So even your residual milk in your milk jugs can cause contamination and smell and odor and color. And unfortunately, what you get usually at the end is usually of lower value than what it started from because of this limitation that you're just melting everything down together. In chemical recycling and biological recycling, They're utilizing technologies that break the bonds to much easier to process smaller molecules that can then be separated and purified out, overcoming the food contamination, the color, the adhesives, the dyes, all these things that are in our waste streams.
Among the range of techniques under development are methods of breaking plastics down by naturally occurring enzymes and bacteria, as well as simple heat. Each method has its own strengths and weaknesses, and understanding how each can best be used requires consideration of what plastic itself is.
Plastics are comprised of what's called polymers. They're a series of molecules all covalently attached to each other, so they make these super long macromolecular chains. And when those chains are all existing together like a bowl of spaghetti, they provide really strong mechanical reinforcement to them while still being super flexible and really lightweight. So when they were discovered, they were one of the most remarkable discoveries of all time. I mean, no one had ever seen something like a piece of plastic. And that's why they entered in our world into such a rapid fashion and became very, very cheaply made and easily disposed of, and life seemed to get better. But that being said, we now are in this crisis in that we produced and used in such an alarming rate that we're now completely inundated with this material that we're deriving from petroleum oil. Most of our fossil fuel consumption is actually coming from the production of these plastics, which is why it's becoming an energy crisis and not just this waste crisis.
But if plastic plays such a large role in environmental harm, why not simply eliminate it?
More and more cities across the country are banning plastic straws. A ban on single-use plastics such as straws, cups, and plates.
A new plan to ban plastics, ban those products forever.
To calculate the environmental impacts of any material, experts use a system called life cycle assessment. And when applied to plastics, the results may come as a surprise.
A PET water bottle has about a third of the carbon footprint of a glass container and about half the carbon footprint of an aluminum container. So if we were to eliminate all plastic water bottles and replace them with an alternate material, we're looking at larger environmental impacts in other areas. And this is where life cycle thinking comes in our environmental decision making. We aren't going to ban our way out of this. We need to be employing new technologies, creating new pathways for manufacturing in order to solve this.
I think it's important for us all to keep in mind that plastics are not evil. From an environmental perspective, plastics are extremely lightweight when we compare it to things like steel and glass. And that makes traveling in an airplane the same as in a car, the same as in a truck, to be much more fuel efficient. They also make our food last much longer, which food waste itself is a massive environmental challenge as well.
And while there is a very negative connotation associated with plastics currently, I think we need to remember what they've done in terms of hospital-acquired infectious diseases. So now when you enter a hospital, everything is very sterilized rather than metal tools that did not have the same capabilities. Our homes are more durable and energy efficient. And I think that this mentality that we need to shift away, that buying yogurt in a glass container is somehow going to be better, doesn't really make a lot of sense when you consider that glass container goes into the same recycling bin, and most of states in the US do not recycle glass. And when it is recycled, it's usually ground down and placed into concrete. You're kind of in that same circle that you're in with plastics recycling. It's the same conundrums. Is this true circularity? Plastics are making things better on an environmental and social impact, but it's the pollution and energy that's used to make them that is the problem we're trying to address.
So what we're doing here today is looking at several different enzymes that haven't been tested before, and we're trying to find out if they're active at degrading or hydrolyzing PET plastic. And so the way we find out whether there's success or not is we're looking for the monomers that are broken off of the polymer. And these enzymes, what they're going to do is they're going to start breaking those bonds and releasing the smaller fragments. And we can quantitate that amount, and then it gives us a comparison as well. And so these are really small. This isn't going to get us very far trying to tackle the global plastic waste problem. But this gives us baseline data. And then the next step would be to scale up to at least a liter. And that starts to look a lot more like what an industrial or a commercial recycling facility would look like.
There's a large community of researchers, scientists, engineers in the world today who are thinking about how do we start over on plastics design. In the Bottle Consortium, what we're trying to do is marry that concept of starting over, making polymers that are inherently recyclable, with advanced recycling of today's plastics, where we can take mixed plastic waste. We can use chemistry to break those down with a figurative hammer, and then use biology through a microbial cell factory and make building blocks for polymers that are inherently recyclable by design.
In practice, this means that mixed and degraded plastic waste can be transformed into new polymers, like polyhydroxyalkanoates, commonly known as PHAs, or bioplastics. PHAs have the benefit of being both compostable and recyclable, and in some cases, even marine degradable. So if it were to end up in the ocean, it would dissolve into harmless organic materials in a matter of months or years, rather than centuries or millennia. The downside to bioplastics? They're typically made from plants like corn or wheat. To scale this up for mass production would require diverting a massive amount of agricultural resources from an already strained food supply chain. But what if this could instead be accomplished using today's waste plastic?
Circularity can be redefined, and circularity doesn't need to be polyethylene to polyethylene. It can be polyethylene to 35 different products. We've even looked into technologies of how to digest some of these structures into vitamins and health supplements and animal feed. And I know that sounds kind of like sci-fi future, that we'd be eating plastics, and that might scare people, but the reality is they are the same carbons and structures that you're putting into your body a lot. And so this is a very, very futuristic way of thinking, that maybe one day plastics become food and not the microplastics in your fish that we're all eating. I mean, that it can actually become real proteins that can enrich our diets and have this now food source available to us in a world where food is starting to become a crisis. And so it's a novel way of thinking about it, and that's kind of how I picture a world for recycling, that there's tons of pathways for these carbons to go into, and we don't need to just limit them to plastics.
But while these technologies form a roadmap for the future, advanced recycling is taking a foothold in the present. And among the first to reach industrial scale is San Francisco's Brightmark.
Consuming less single-use plastics is essential. However, many of the uses of plastics are either difficult or irreplaceable. In fact, 2/3 of the overlooked plastics that are created are in areas like healthcare, textiles, electronics, and the automobile industry. There are not any really good alternatives for those. So for the first time ever, we can take those necessary plastics, particularly the hard to recycle 3 through 7 plastics, and convert them back into useful products.
Brightmark's plastic renewal technology is based on pyrolysis, a process of breaking chemical bonds by applying heat in the absence of oxygen. It's a technique that's been known for over 1,000 years and is the basis of producing charcoal from wood. But when applied to plastic, an entirely different result is achieved. It turns back into the original petroleum it was created from. Whether that's used for fuel or to produce new plastic products is a question of market demand. And it's a question that will begin to be answered in rural Indiana as Brightmark's first major facility comes online.
What's really amazing about us nearing completion in Ashley, Indiana, is for the first time possible, this process known as pyrolysis, which has had a lot of hope for the future, will finally be demonstrated at a scale that can work globally. 100,000 tons of plastics a year is an awful lot. It's very scalable. So as we complete that project, we're at a moment where the world can finally see there is a viable solution to all the plastics we have out there.
We're located here in Ashlyn, Indiana, which is roughly halfway between Chicago and Cleveland. Within about 170 miles of here is a pool of material that's right now heading to the landfills. You can see here, this is where we store roughly 3 days supply of feedstock, which is around 900 tons of material. And we get it generally from recycling centers where they'll pull out the valuable materials, and this is the stream that they can't handle. These are general recycling bales where you have containers, film, bottles, different plastic parts. So pretty much everything you see is a candidate for our process. And they'll bring the material down into our processing system where we have 2 separate mirrored lines where we can process roughly 12,000 pounds an hour on each line. And then it can be pelletized into a dense pellet. The pellets then come up this conveyor and they drop into a hopper where they can feed right outside to the plastic conversion units. And then we have a fully enclosed, oxygen-starved vessel where we thermally break apart the plastic components into smaller pieces. And then we capture that vapor and condense it down into a liquid, which is a light, sweet crude oil. This large column is a distillation column. So the heavy stuff comes off the bottom, the middle stuff comes off the middle, and the light stuff comes off the top. So it's just old school chemistry, basically, that we're doing at an industrial scale.
Pyrolysis isn't the most sophisticated form of advanced recycling. Compared to emerging technologies like enzyme or biological recycling, it's significantly less energy efficient. But it is available today. And more importantly, it presents a viable market for taking plastic waste out of the environment. While critics contend that turning plastic into gasoline or diesel fuel isn't true recycling, it's impossible to overlook the fact that fossil fuels will still be in use for years to come. Pyrolyzed fuels offset the need to extract crude oil, and that could be exactly what industries need while transitioning to renewable energy.
We're creating value so that plastics don't end up in landfills and in waterways and in oceans. Is the end state creating transportation fuels what I want? Absolutely not. Our goal is to have zero combustible products that we produce. It's a journey, though. If it is in people's interest economically to recycle plastics or anything, and it creates a better environmental outcome, I think you end up with long-term economic sustainability for sustainable solutions.
But regardless of which method is used, mixed and degraded plastic waste has no future without advanced recycling. And nowhere is more of it to be found than in our oceans. Organizations working on ocean cleanup are often met with skepticism. Critics point to the need for global policy changes and industry regulation to stop plastics from ending up in waterways. But that's only half the equation, because even if all plastic pollution ended today, the 5 trillion individual pieces of plastic in our oceans would continue to multiply. Why? Because they're fragmenting. And while many types of marine debris will float on the surface and eventually be carried to shore, fragmented microplastics spread throughout the water column, poisoning marine life and disrupting the food web, in addition to being difficult or impossible to recover.
At this time, a lot of the plastics we find are still intact. We can pick them up. So if you pick up a 5-gallon bucket that weighs 2 pounds, you're removing 2 pounds of plastic in about 2 seconds. If you wait 10 years or 20 years, that plastic bucket is now thousands of fragments, and it's nearly impossible to clean up at that point. And so we've got a limited amount of time to work with before these materials degrade and really become a much higher hazard. So we feel like we're in a race to get this material off the beaches and out of the ocean.
Scott Farling is a co-founder of the Ocean Plastics Recovery Project. His team is leading a series of expeditions to recover marine debris from the remote wilderness of Alaska.
This is Katmai National Park, and it's a pretty spectacular place, and it's been heavily impacted by plastics. There are no people here, but the plastics make it here. They come up across the North Pacific, through the Gulf of Alaska, and get trapped on the beaches. And so Our goal is to clean this park. We've been working at it for 2 years now. This is our final expedition to the park. We expect to collect about 50,000 pounds of material off the beaches. And then we've partnered with a number of recyclers, from mechanical recyclers, chemical recyclers, conversion technologies, to take those materials and get them back into the economy.
Cleaned up all this already. Yeah. Cleaned up all this already. There's a large piece of marine debris that I just want to get my eyes on, hopefully through a drone flight, right around there. It might be too big for us to handle. It might need to be cut into smaller pieces, but I think the first thing to do is get eyes on it.
After decades as a chemical engineer in the recycling industry, Scott and his team are moving beyond simple beach cleanups. They're creating a blueprint for organizations and governments around the world to process marine debris. How to effectively recycle degraded ocean plastics is not an easy problem to solve. But in doing so, there's a massive potential for an entire field of emerging technologies and an entire generation of young minds to develop them.
We're really hoping to educate the future generation to really provide the workforce to build out our recycling infrastructure in the U.S. We don't have that. It's not a formal education program right now for recycling, and we're really trying to build that component. On this trip, we've got students from Western Washington University and Oregon State University. One of our team members here has led their group to redesign their pyrolysis reactor, and we're getting much better performance now, and so we're ready to start running ocean plastics through it. They'll be taking our degraded polyethylene and polypropylene materials and converting that to diesel fuel. And then we also bring industry professionals. On this trip, we have a marine biologist, we have a researcher from University of Berkeley, we've got a scientist that's helped develop some sensing technology for determining what types of plastics are using a handheld device. It's really important for us to bring all those people together to do this work together and learn from one another.
Oh, yeah. Perfect.
And so it's really cool to see the chemists and the biologists and the chemical engineers and the polymer composite engineers all come together. These are some of the toughest, strongest, smartest women, and there is so much diversity in backgrounds and methodology and knowledge here. And so it's been a lot of sharing of that knowledge.
When we first pulled into Hallow Bay, like our first stop, it was absolutely beautiful. You could see this perfect glacier in the background, these like nice, tall, waving mountains. You could see bears just on the coast. But when we actually got onto the skiff and got onto the coast, there were giant lines, lots of nets, and there was just tons of actual rigid plastics. And I remember one of the ones that really stuck out was this very, very brittle pallet that we literally had to excavate out of the ground. But as we were trying to excavate it, it just kept breaking into smaller and smaller pieces. It's a very sobering experience seeing such a beautiful place kind of tarnished by our inability to control a problem that we created.
Given the scope and impact of plastic pollution on the environment, is it unreasonable to be optimistic? Is it too late for recycling? For those working to solve these problems, the answer is no. Now is the time to reinvent recycling.
People really shouldn't look at the solutions for recycling in terms of the technology that was available 10 or 20 years ago. They really need to be focused on the technology of today.
And we're seeing this huge boom of just ingenious ideas coming out to sort plastics better, to clean them better, to lower water usage. And so innovation, I think, is really driving so much in this space, probably more so than thinking about how to get rid of plastic. It's really, how do we manage this forever moving forward?
Big problems require persistent optimism on a long-term basis. We've got a long way to go, but I'm optimistic we'll get there.
I think we very much can win this race.
No one organization, company, research institution, or university is going to solve this problem alone. It will require many disciplines, not only science and engineering, but policy, social science, education, all at the table together.
The good news is that there are a lot of technological answers to these big environmental problems that we have right now. The question is, do we have the will and the courage to break through the inertia to transition toward those more environmentally friendly technologies?
Back at Oregon State University, Ani and Maddie prepare to test the first batch of marine debris in their newly designed reactor. The results will help determine whether advanced recycling of ocean plastics will remain a theoretical hope or a practical future.
With marine debris, we think a lot about rural and island communities. The places where plastic washes up are going to be the places with the least amount of infrastructure to handle that plastics problem, which is why we work so hard to make our reactor really simple to use. And because it's so much easier to reproduce our new version of the reactor, we do a lot of proof of concept of what about plastics that are washing up from the ocean. Could that go to a rural or island community? And so we are testing things like what happens when we have barnacles on our plastic, what happens when we have salt water on our plastic, what happens when we have seaweed in our plastic. And all of those things we will work to test, both with plastics from this trip and other sources of waste plastic.
The tests are a success, but it's only one step in a very long journey. And it may very well be that the scientists who complete this work have yet to be born.
The younger generation is eager to help. I work with elementary and middle school kids all the time, and the number of questions they have when you say, "Oh, I turned plastic into diesel," it's like magic. Their eyes light up. They have endless questions. So while I may not be able to pick up all the plastic in the world, if I can excite 5 more kids once a year that there are people working on this problem, so keep your hopes up, that will be a good day for me.